So the main discussion last week was related to how to find maximum shear stress. We said that the maximum normal stresses are the stress tensor, basically. Oops. So this is the stress tensor, and we said that this is the maximum principal stresses, and this would be the maximum normal stresses that could ever exist. Now, on this, on the plane, basically the planes for them are basically going to be N1, probably just write them as vectors, N1, N2, and N3. So N1 is the plane where sigma 1 will exist, sigma 2 will exist on N2, and sigma 3 would exist on N3. So this is the maximum normal stresses. On these maximum normal stresses planes, you don't have any shear stress. However, there exists some maximum shear forces or maximum shear stresses that lives on a different plane. So the maximum shear forces, we said, since we are going to agree that sigma 1 is larger than sigma 2 and sigma 2 is larger than sigma 3, then the maximum shear stress is going to be, I'm going to call it tau S max or TS max, whatever you prefer to call it, should be sigma 1 minus sigma 3 divided by 2. And this, or the plane where this maximum shear stress exists, is going to be NS max. So this vector, and this is plus minus 1 over square root of 2 of N1 plus minus N3. So it does not exist only on one plane, it actually exists on a variation of 4 different planes. And these are all the planes where the maximum shear stress exists. And on the same plane, you don't have, in the general case, you don't have normal stress, zero normal stress. You have some normal stress. So you probably can call that sigma N or sigma S max is going to be sigma 1 added to sigma 3 divided by 2. And obviously both of them exist on this plane. And then we said there is an equation for equilibrium, just like we have equilibrium of forces, we also have equilibrium of, I'll just move this slightly upward. Just like we have equilibrium of forces, we have also equilibrium of stresses. So in terms of the stress tensor, if you like, Tij, so the derivative of Tij with respect to xj added to the density multiplied with body forces should be equal to rho multiplied with acceleration at the direction I. So this is basically 3 different equations. If you expand that, you will get the 3 different equations. We solved one quick example using this equilibrium equation. Okay, so this is pretty much everything we discussed in relation. Now, this is what we have, or everything we have discussed mainly last week. I'm going to probably start in a simple case, possibly. And then from this simple case, let us move into something more complex. I mean, let us start the discussion from something simple. And then we go ahead and discuss something more complex. Now we have some steel section. And this is quite a common type of section. Let us assume that this is the section you have and you want to design. The only difference between this section and any standard section you design is the fact that the load can happen in not quite a standard way, not a traditional way. So in a very standard cross section, or the type of load you have for this type of cross section, you would be expecting loads active in the axial direction, probably loads active in this direction, or probably some loads applied in the transverse direction that are applied to the axis and in this vertical direction. You may, in some occasion, have this load might not be applied right at the center, so it might be applied at some distance from the center of the cross section. And then in this case, you may have some bending moments. You can also take, or torsion, you can also take care of that. Now, how about you apply the load in a completely completely non-traditional way, and you have probably some inclined loads applied right at the body of this cross section, or probably applied at this joint here, or at this angle here, or probably applied on the edge of the web. I mean, these type of possibilities will result into some stresses. So what stresses would you design for? And what stresses would you consider more critical? Now, think about it. The material properties are going to be homogeneous. So basically, no matter in which direction you hit this cross-section, you pretty much expect the same material properties to happen. And by same material properties, I would mean the same yield strength. So the yield is going to be the same for any direction you hit this material from. Now you have some loads, and you can now compute the stresses, and you want to check if this cross-section is going to yield or not. I mean, let us simplify the discussion. And we want to figure out if this cross-section is going to yield or is not going to yield. And we want to check that. I mean, the yield strength, you get the yield strength by applying some, you have some material sample. If it is a steel, for example, you have some steel bar, and you do the uniaxial test on that. So you apply some axial forces on that, and you keep pulling this bar from each side by increasing the value of F. And then at some point, of course, the stress is going to be F divided by A. So this is sigma. And then you look into the stress, how it changes with the strain. This bar is going to become longer and thinner. And then at some section, you don't know, usually is going to be the midsection close to the middle, is going to become quite thin and is going to break. So if you look into the relation between the strain and the stress, you'll see that this is going to increase in a relatively linear way, and then is going to yield, and then is going to expand quite quickly. Once you get this necking behavior, this is going to start to move quite quickly faster, and then at some point it's going to break. This is the section for the break. So this is this point there. So you will see that at this point, and then at some point it's going to break. Now, if you look into this curve, this is quite some complex material behavior, and this complex material behavior is only happening in one direction. And it is going to distinguish, I mean, if you look into steel, you are going to distinguish between two parts of material behavior. This part, we call it elastic part. So this range is the elastic range. And then beyond that, we call it the plastic range. Or this part can be linear and this part can be nonlinear, but there is a big difference between linear and elastic. So these are two different concepts. I'm going to come to that in a minute. But this part we call the elastic part, and this part will end with the yield strength. Now, how to identify the yield strength? There is quite a lot of details into this curve. I'm not going to get into that for the time being. I mean, if you're interested, you can ask me. But we assume that, I mean, we try to identify this point where the elastic range would finish. We apply some safety factors usually. So we take it slightly before that, and we say that this is the yield strength. So this is sigma y. Now, if you look into sigma y, which is compared to this number here, you'll see that this is a normal type of stress. This is not a shear stress. And because of that, you can compare sigma y. You can compare sigma y to the maximum principal stress. So if this is larger than the maximum principal stress, sigma 1, then in this case, you know that the material is safe. Now, you can, I mean, this is the type of cross-section we are discussing here, just applying non-conventional loads to that. But think about something more complex. I mean, think about a 3D object that you really want to design, and this 3D object would be not quite homogeneous. This 3D object would be subjected to some acceleration, is going to subject to some thermal stresses, and is going to be also some extra forces applied to that. I mean, if we go back to this space industry point, for example, you can think about the type of thermal stresses you have in there due to the exposure of one side to the sun and the other side is not exposed to anything. The difference between the temperature in the face that is exposed to the direct sunlight and the one that is in the shadow is going to be huge, and is going to result into some significant thermal stresses. For example, thermal stresses are not going to behave in a regular way. I mean, thermal stresses are not regular type of load that is going to be described quite easily, for example, in the Eurocode. On top of that, you have quite a lot of other forces that are active on this object. And then you have a combination, a really complex combination of material behavior and stresses, normal and shear, and you really need to understand how they work together. So it's basically how to compare them together. So it's not going to be just one number to compare to the other number. This is a set of actions that you need to compare together. And it's going to be up to you to do this type of comparisons. So this is really something to think about. Okay, so if you look into this comparison, this is pretty much the simplest possible comparison you can do for the stress. And it assumes that the material is going to only fail through the normal stresses. And this is called Rankine criteria. So I'm going to come to the lecture today and get you into discussing different type of failure criteria. So as I said, the sigma 1 smaller than sigma y type of comparison is called Rankine, but this is the simplest possible criteria. The material behavior can be a lot more complex because the normal stresses usually would be accompanied by some shear stresses. For example, if you look into the plane where you have the maximum shear, you have also normal stresses. Well, if you have this combination of stresses, which one is going to be more critical or which one you should be designing for? All these type of questions are going to be the questions you ask yourself when you design something. Luckily, there's several equations, so several criteria, like what Carl mentioned, that can compare these type of numbers together, and then you know that the yield has happened or not. Okay? Because in the most general case, you have a stress tensor that will include many numbers. So it's going to include a lot of non-zeros, sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, 2, 2, and 2, 3, and sigma 3, 3. And you have this bunch of numbers, and you have this yield strength, so how to compare them together. So there will be several criteria that you can use to do the comparisons. And I'm going to discuss only the ones that are relevant to structural engineering, probably mechanical engineering as well, they will use them. But there will be other criteria that you can learn on your own if you need them, and they are not much different from what I'm going to discuss today. Okay, so first of all, I'm going to talk briefly about the material behavior. If you have this uniaxial test, so you have this bar, and you have some forces applied to this bar. This bar is going to stretch, so the atoms or the particles are going to move relatively to each other. As long as these particles will return exactly to the original place once you release them, you call this elastic region. Once there will be some relative displacement within the particles, so this layer of particles has moved relatively to this one, and this is a permanent deformation, you get into the inelastic region. I'm going to say inelastic here because I'm going to talk about situations where this is going to break altogether. So it's not just going to move or deform permanently, it's going to break. So for ductile material, this is going to move. For brittle material, this is going to break. So anything beyond the elastic range is going to be inelastic, so break or plastic. Now, if you look into the material types, you see that there's a range of material behavior. We try to classify them as ductile material or brittle material, but this is quite dependent on the temperature. So if we talk about steel, for example, steel is ductile if the temperature is really average, I mean the type of room temperature you are familiar with. But if you drop the temperature and you drop it really low, I mean, we're talking about minus 100, minus 200 degrees. In this case, steel is going to become a brittle material. And this is, again, something I said. I mean, if you design for non-conventional scenarios, steel is quite a brittle material. If we drop the temperature to, I don't know, 10 Kelvin, for example, or minus 260 degrees Celsius, for example, and this range will get steel to be quite brittle. But assuming that we're talking about the room temperature, metals in general are considered to be ductile material. So for example, this is how copper is going to behave. About softer brass, this is the range for softer brass. If we look into steel, there's a range of steel that can we look at. So, and this depends basically on structural steel or not. In general, this would be the type of structural steel that we use. So these two types of steel, so medium carbon steel. And if you look into the behavior, you'll see that there's no straight lines in there. I mean, we try to identify a straight line right at the beginning of this curve. For steel, we have something distinguishable. But for different type of alloys, you don't have that. And this elastic range would expand beyond the linear part. So this is why I said nonlinear doesn't mean plastic. So for example, if we look into softer brass, for example, it does actually behave in a quite nonlinear way before it starts to get into the plastic range. So all the way up to this point, I think, or probably somewhere just before that, you still have an elastic range. So the material is going to restore to the original situation immediately after you release the stresses, although it is actually displaying some nonlinear behavior. So be careful. Nonlinear doesn't always mean plastic. And if you look into, for example, if you look into different type of polymers, different type of polymers would behave certainly in a nonlinear way. For example, is going to behave like this. And when you release the stresses from the polymer, it's going to restore all the way back to zero stresses and zero strains. So be careful about what you consider nonlinear and what you consider plastic. So the other range or the other extreme of material behavior is going to be brittle material. So brittle material is something like concrete or glass or stone. These type of material, they would break immediately after the elastic range. So you apply some stresses. The stresses are going to result into small deformations. Usually deformations are quite small. Now, if you look into the range of strains we're talking about for brittle material, is a lot smaller than the range of deformations we talk about in elastic material. I mean, you see we're talking about 50% type of deformation. Here we talk about 1% type of deformation. And glass, I mean, certain type of glass will break way before 1% deformation and break quite quickly. If we talk about cast iron, for example, cast iron is quite brittle as well. Now, for brittle material in general, one observation is they usually perform much better on compression compared to tension. So tension is usually weak in brittle material. Compression is usually strong. And you can expect that in glass, for example. Glass under compression can take a lot of compression and it's really difficult to break. But if it is tension, it is a lot more quicker to break. And see, if we're talking about the glass in compression, we're talking about, I mean, this is for a specific type of glass. There will be other types of glass, but if we look into this, for example, type of glass, we're talking about 1,200 megapascal. And this is comparable to steel. So glass, for example, can be quite strong in compression, but once you get into tension, you'll see that this is much, much smaller. So it will break very quickly if we're talking about design using glass, for example. So this is why you cannot, I mean, this is usually why you cannot use brittle material to work on its own. So for brittle material, for example, concrete also is a brittle material. When you use a brittle material in your design, you would need to support it using some other material as well. So for concrete, you would have to add some extra steel and make it reinforced steel or reinforced concrete. If we're talking about the glass, you would also reinforce glass as well. You can add different type of polymers or different type of steel to reinforce glass as well, if you want to use it for surfaces that can take loads in different directions. All right, so I'm going to just give you two numbers here. Sigma y is going to be the yield stress, and sigma ultimate is going to be the ultimate stress. So the ultimate stress is the stress where the material is going to break, and the yield stress is the stage or the point where the material will going to change behavior from elastic to plastic. So this is the two numbers I'm going to need for what I'm going to discuss next. But as I said, I just want you to imagine that the picture is slightly more complicated than just these two numbers. Now, the ultimate stress is going to be the point where the material is going to break. So if we look into this brittle material, this is sigma u. But for brittle material, sigma u is pretty much equal to sigma y. So immediately at the point where you get the yield, you get the break as well. So you get the failure happening at the yield point. If you look into the ductile material, you see that the yield strength is probably somewhere here. The ultimate stress is going to be the maximum amount of stress, probably is clearer here. So if we look into steel, you will see that the yield stress will happen here. This is sigma y. The ultimate stress is the maximum amount of stress the material can take before it fails. So this is sigma ultimate. So slightly higher, well within the plastic range, and immediately after that, the material would start to fail. So the necking behavior would start to become quite clear, and it's just going to lead into failure. So these are the two numbers I want you to remember. And when I'm going to discuss failure, I'm going to discuss failure relative to these two numbers. Okay. The failure criteria I'm going to describe next are basically based on observation. There is no scientific reasons, or there is no theoretical reasons why we pick them. We pick them only because they describe the material behavior accurately. So we are going to see that Tresca, von Mises, for example, or Rankine criteria, they are useful for certain scenarios. In certain scenarios, they would really describe the material behavior. In other scenarios, they probably don't describe it, so we don't use them. So there is no theoretical reasons why we develop this criteria. This is basically based on observation, pure observation. So they are experimental and they agree with reality. So this is why we use them. If they stop agreeing, we don't use them. So this is why we have several criteria to judge the failure, because every certain scenario you'd find a different criteria that would be relevant. This convention where sigma 1, sigma 2, and sigma 3 are going to be put in this order. So sigma 1 is larger than sigma 2, and sigma 2 is larger than sigma 3. This is the order, and this is the convention that I've proposed in the lecture number 2, or lecture number 2 and 3. And this is the sort of convention we are going to stick with. I'm not going to change that. Okay, so everything I'm going to discuss next will be based on this convention. Okay, so the simplest possible way to compare failure is going to be this equation here. You compare sigma 1 to sigma y, or sigma 1 to sigma ultimate. Once sigma ultimate would get into sigma y, or sigma y would become equal to sigma ultimate, you would know that your material has failed. There's no way that the material can continue or you can continue loading the material after sigma 1 has reached this point because the material has failed. So when you make your design, make sure that this number is satisfied. At least, I mean, you need to usually apply some safety factors in there. So you reduce the sigma ultimate. You don't take exactly the same sigma ultimate you get from the experiment. And you also assume that this is going to be the maximum loads you have. So you try to calculate the maximum possible loading scenarios you are going to have, and you pick the most critical one, and you take the most critical point, and at the most critical point, you calculate the principal stresses, and you take sigma 1, and you compare it to sigma. Okay, so as I said, this is quite intuitive. This is kind of the most obvious thing to do. But there will be scenarios that this is not going to describe the behavior, because usually shear and normal stresses, they are active together. So they work together, especially when we don't have very simple loading cases. So if you have the axial loads case, well, you don't have any shear, or you have some shear, but this is not going to affect the critical behavior. But once you start to get into complex loading types, then in this case, this is not going to work. So you need to think of something else.